I have the pleasure to announce the second speaker is Timon Peters. Timon studied civil engineering and architecture in TU Darmstadt, where he now is also a researcher, looking into thin glass, but also looking into inclusions in glass. So today he will present about his work in inclusions in glass. So Timon,
thank you.
The floor is yours.
So, hello everyone, my name is Timon Peters. I'm from the Glass Competence Center at TU Darmstadt. We've seen 6 presentations from our institute at this conference before, so this one is the 7th. And my project is glass inclusions, and especially a focus on nickel sulphide inclusions, which can become critical in glass. I will talk about 2 things. First of all, the prevalence of inclusions, and then also how you can identify them visually without destroying the glass. So why do we do this research? Generally, if you get glass from a manufacturer, you will find a lot of small defects. That's because if you produce glass, you will always have those defects, and you will only sort those out that can become visible to the customer. So that's usually around 400 or 500 micrometers, after which you sort inclusions out, and everything below stays in the glass. But there are some inclusions that can become critical even below this size. We can see on the right some stress plots from inclusions taken with cross-polarizing filters, and we can see that around some of these inclusions there are really high stress concentrations. So what is critical? One way of being critical is being visible. There are still some inclusion types that are visible below 500 micrometers in diameter. But what's even worse is inclusions that that create enough stress in the glass to make the glass break, especially if it's tempered. On the left one, we can see our standard zirconia stone that is created by the dissolution of the glass melting furnace itself. This one usually creates stress immediately, and it will lead to failure of the glass immediately during pre-stressing. But what's even worse is nickel sulphide, which is shown on the right, which has a time-delayed expansion and a time-delayed stress creation. Here we can see a nickel sulphide inclusion that had an expansion of 0.51%, which is already at the upper limit, but even at 2, 3, or even 1%, an inclusion can create enough stress in the glass to make tempered glass fail spontaneously. We can see that on the right, on top, there is an inclusion that caused the fracture that we see on the bottom. Currently, the industry standard is to do the so-called heat soak test. I recreated the heat soak test here, and we can see that after about 2 hours, cracks start to form around the inclusion, and those cracks grow, and probably after 3 hours, if the glass was tempered, the glass would break, and we would lose this piece of glass. And in the worst case, this same thing would happen over years in the facade of your building. What's also a problem with nickel sulphide inclusions is that the tempering process resets the phase transition of the nickel sulphide inclusions. On the left, we can see a graph where a nickel sulphide inclusion was cycled through temperature changes, and we can see the inclusion expand and contract again and again. So every time we temper the glass, we reset the time that it takes for the inclusion to reach the critical point. On the right, we can see one of these inclusions that I had put in tempering oven, and we can see that the cracks completely closed, and they're only visible because some diffusion had happened and some debris or whatever accumulated in the cracks before the cracks could close. So how many inclusions do we have, and how are they distributed in size? For this, we scanned 23 tons of glass. We had a prototype of an industrial flat glass scanner from an industry partner, and we used it to find the inclusions in the first place. And then I spent several weeks, months, years microscoping all these inclusions. And we had about 2,300 inclusions, so 1 inclusion per 10 kilos of glass. And we were only looking for solid inclusions above 50 micrometers because nickel sulphide usually only becomes critical above 50 micrometers, and it's usually a solid inclusion, so no debris floating around or local crystallization of the glass or anything like that. We can see that half of the inclusions are smaller than 120 micrometers, and only a quarter is bigger than 200 micrometers. And this applies to all inclusion types to a varying degree. So bubbles, nickel sulphide, whatever, they always have approximately the same size distribution. If we do a logarithmic plot of this, we can already see that the quality control system of the manufacturers, the glass was from 2 manufacturers, it kicked in at around 400 micrometers and took out all the inclusions. And if we go below 400 micrometers, we get a really nice exponential distribution of inclusion sizes with a fit of 99.7%, which is pretty good, and allows us to predict what smaller inclusions we have to expect. We can expect that there are many more smaller inclusions below 50 micrometers. This can already be seen if we look, for example, at bubbles that accumulate small stones of 10, 20, 30 micrometers on its surface, and we find a lot of these. So we have many spherical inclusions in our glass that could be nickel sulphide. In this case, 3 of them are nickel sulphide, and I will quickly go through some photos and some data on all of these inclusions shown here and how we can differentiate them. The first one is very obvious. It's the bubble in the glass. It's usually easily identified by just shining light through it from the back. Sometimes this doesn't work. For example, if the inclusion behaves like a lens on the left, we can see that even if we have a light behind, the light might go off in another direction and the inclusion might look solid, but most of the time you can just shine light through it and immediately see that the inclusion is a bubble. Of course, you also have filled bubbles. On the left, there's a bubble that's filled with some kind of salt, and these bubbles can change also, for example, before and after tempering. On the right side, I tempered a bubble that is filled with some kind of substance that we haven't identified yet, and it completely changed shape during the tempering of this bubble. We can also see connected bubbles, either emitted from an inclusion, for example, a silicon inclusion, where the silicon dioxide of the glass is reduced and carbon dioxide is set free and comes out of the inclusion, or on the right side, a bubble that has probably just stuck to an inclusion in the glass. So let's go first at silicon inclusions. Here are 2 pictures of silicon inclusions. What you see sticking out from the inclusion is graphite. So that's the carbon that reduced the glass matrix around it and created the silicon metal. We often see cracks around silicon inclusions, and we see very characteristic small bubbles on the surface. But what's even more characteristic, and what usually always helps to identify a silicon inclusion, is this almost scratched surface that looks totally different from any other surface of inclusions that we usually find. The next type of inclusions we find a lot of is this type of inclusion. It has this small zone around it where particles are flaking off. And in literature, this inclusion is often described as iron. Why iron? Well, if you hold a magnet to it and it sticks to the magnet, it must be iron. But somehow, at the same time, in literature, you also find information that no one has been able to recreate iron inclusions in float glass, because the iron dissolves immediately. So what's the problem here? Well, it turns out it isn't iron. It's actually nickel and an early stage of nickel sulphide. How can we prove this besides chemical analysis? Well, if you don't just have 1, 10, or 15 inclusions, but you have thousands of inclusions, you can find every stage between the nickel metal and the final nickel sulphide inclusion. So you can see the whole transition from the metal taking up sulfur and ending up as the mature nickel sulfide inclusion. And that's what we are getting to now. This is a nice picture of a very characteristic nickel sulfide inclusion. First of all, you see this gold-purple color. You see it on most of the nickel sulfide inclusions, not all, but a lot of them. But what's even more characteristic for nickel sulfide is this fish scale-like surface structure that looks just like little flakes, but if you zoom in at those flakes, you can actually see that they are small crystallites that have formed. You can see the crystal lattice on the surface of these crystallites. Here you can see it even better under very high resolution. And this photo was taken through the intact glass, so you could theoretically assess your glass if you just look closely enough and directly determine that this is nickel sulfide because of this characteristic crystal lattice structure. Of course, nickel sulfide can also look different under your microscope. This is an inclusion that has been taken after a case of spontaneous fracture. And you can see that the inclusion had reacted with this surrounding air, and some kind of green, moldy surface structure has formed. And also, the scales aren't visible that well anymore. Also, what you often find is, due to the fact that the thermal expansion coefficient of nickel sulfide is bigger than of glass, the inclusion will contract more than the surrounding glass, and a void will form around the inclusion, and this may fill with some kind of salt to a varying degree. On the left, it's just a bit, and on the right, the void is almost entirely filled with salt. So sometimes you also find that, and then you need to be careful when you try to identify the inclusion. You also often find the inclusions with cracks around them, and especially if you look from afar. For example, on the one on the left, if you look from afar, you might not immediately recognize that this is a round spherical inclusion, but it may look like some kind of stone if you just have the contour of the inclusion. Also, the cracks that form may sometimes fill with some black matter that we haven't identified yet, but this also makes it difficult. Another thing that we discovered is that nickel sulfide can change its appearance before and after pre-stressing of the glass. So here you can see two cases where I tempered the inclusions. And on the left side, for example, you can see a nickel sulfide inclusion with open cracks and almost no visible gold-purple color. And after tempering, the cracks completely closed, and you will see much more of this gold-purple, greenish color effect on the surface. And on the right, you can see the salt that's filled the void around the inclusion, which has become much more pronounced after tempering. And finally, another way to identify nickel sulfide inclusions for us is the shape. If you, for example, try to differentiate nickel sulfide from silicon, silicon has a melting point of 1,410 degrees Celsius, so it will solidify far inside your glass oven, whereas nickel sulfide, depending on the exact composition, is always far below 1,000 degrees Celsius, so it solidifies during the stretching of the glass. That's why you can very accurately predict the shape of the nickel sulfide inclusions in relation to the thickness of the glass, which you can see on the right. The 10 millimeter is almost perfectly round, whereas the 2 millimeter is very elongated. So in summary, there are exponentially more small inclusions in the glass than large ones. Inclusions of the same type can look very different, but if we know certain unique properties, we can always differentiate them without destroying the glass, and maybe in the future have systems where the glass is checked down to a size of 50 micrometers and only the critical inclusions are thrown away and everything else is kept in the glass, which would be very efficient for the glass industry. And outlook, we need more research on the statistical fracture risk in relation to this surface structure of nickel sulfide. So far, we only have general information on the fracture risk, but not in relation to the actual composition. We need to correlate the surface structure and the composition, and we need better mechanical models, which we are trying to create based on the large sample size that we accumulated over the last years. So, thank you.